Inverse functions, I think, are one of the more difficult concepts in the pre-calculus curriculum. The definition is a little bit subtle, and even if you understand the definition, calculating them is difficult. So let's think a little bit about what an inverse means, really. That's what I want to kind of focus on to start off with. So let's start off with a question. When does a function f does a function f have an inverse function? So let's write the inverse function as f inverse like this. Now, I want to really be careful here. You've got to understand this is just going to be notation for an inverse function. I've not really talked about what an inverse function means yet, but I just want to get this notation out of the way. So this here, this is important, what I'm about to say. This is just notation. From experience teaching calculus in first year courses, a lot of people will incorrectly assume this is exponent notation. It absolutely is not. So this is just notation. This is not 1 over f. No way. So it's unfortunate, I think, this notation, because it's easy to confuse it with exponent notation. So you've really got to know where you're living. If you're living in the world of numbers, sure, this is 1 over f, if f is a number, but if f is a function, this represents the inverse function. So I think this is a bit of a problem for people learning. This is easy to get confused by the notation, but if we're talking about functions, f inverse means the inverse function. So what is the inverse function? What should it do? If there is an inverse function, what properties should it have? So what should f inverse do? What's its job? Well, the basic idea of an inverse is to undo the function. So a function, remember, is like a machine where you feed in a number, an input, and you get an output out. So the idea of an inverse is to reverse that process, to reverse the role of outputs and inputs, essentially. So if we were going to use one of my number line visualizations, so if I think about the function as going in this direction as usual. Okay, so if this is my function f, so over here I've got my x. At this point, well, let's call this y. So we'd write that as f of x normally, but let's write it as y. What should the inverse do? The inverse should send y straight back to x, right? It should reverse the roles of outputs and inputs. So it should do this. That's what the inverse should do. So let's try to write this down a bit more specifically, shall we? More precisely. So for all, what I think we're trying to get at is for all x in the domain of f, I suppose, and y in the range of f, well, if f of x is equal to y, this should be if and only if f inverse of y is equal to x. So this is me just more precisely writing down what's in this picture. So for any choice of x in the domain and y in the range, this should be true. That's what it seems to be saying here. So there's an obvious problem with this in general, and let me show it to you. So a potential problem or obstacle. Well, imagine I have the following. So let's do a specific example, one we've already seen. So let's take the function which is x squared. Okay, so f of x is equal to x squared. So what does that do? Well, if I take the positions minus 1 and 1, and I see where they map under x squared, they both go to the same thing. So this is me thinking about f of x is equal to x squared. So they both go across to 1. Minus 1 squared is 1, 1 squared is 1. So in this case, what do I do? If I'm going to define an inverse, I need to go back in the opposite direction, don't I? So I need something like this. But I've got a bit of a problem, because what's f inverse going to go to? What's 1 going to go to on f inverse? Well, you've got two options here. You either go to 1 or you go to minus 1. You can't go to both. Right? You can't go to both because f inverse has to be a function, and functions can only have one output for a given input. So I've got a problem. If I want this to happen above for any x in the domain, and I make one of these choices, it's going to fail for the other. So I've got a real issue here. So this is a problem. We can't have two values. Can't be two values if f inverse is a function. So before you say just define it as plus minus 1, that can't be a function. That can't be a function because you are only allowed one output for an input. So looking at this, I can see there's no way of sensibly making a choice of the inverse, because I would be forced to choose either minus 1 or 1, and the moment I make one choice, that messes up the other. So this thing wouldn't work, this loop wouldn't work if I chose the other start point. So this is a huge problem. So just as a quick example of that, what I mean is if I was to make this choice, so if I was to make this choice over here, then the loop would work as long as I started from minus 1 and went around to minus 1. It's all good. But the loop will fail if I go here and then back, because I'd end up in the wrong place. So you see, that's what I'm getting at. Any one choice will mess up this picture above. So what I can see from this is there's no chance of defining an inverse function in this case. So this picture tells me there can be no I'll say well-defined. Well-defined means defined in a logical, sensible way without any ambiguity. So there's no sensible way, it's impossible to define this in a way which makes it sensible. There is no well-defined function f inverse in this case. So if I have the function x squared, there's no way there's going to be an inverse to this. So what this really means is the concept can't make sense. Can't make sense. Now, what is the core issue here? You can really see the core issue is the fact there are two distinct values mapping to the same thing over here. That's the issue. And what does that mean? Well, that's exactly the property of not being one-to-one. So here, f is not one-to-one. Not one-to-one. So it turns out that one-to-one actually is the only obstacle to having, or not being one-to-one is the only obstacle to not having an inverse. So here is a nice fact. F admits or has an inverse function if and only if it's 1 to 1. This is a big reason we singled out this property 1 to 1, is because it's totally crucial to the concept of an inverse function. So I think if we have a 1-to-1 function, we know there's an inverse now. Let's be really precise about this. So definition. So I'm going to write down a very precise definition of the inverse function. So let's have f, let f be a 1-to-1 function. We need that. If that's not the case, there's going to be no inverse because of this ambiguity about where things are sent potentially. And let's say with domain capital A and range B. So these are two subsets of the real numbers. So the inverse of, or sorry, the inverse function of f, I should be safe, shouldn't I? The inverse function of f, denoted kind of f inverse, this slightly ambiguous notation, is the function with, okay, it's going to reverse the domain and the range because it's everything done backwards. So it's going to be domain B now and range A such that, so this is the defining property. So it's exactly as we've written before, basically. So f inverse of some number y is equal to x. So it's a bit confusing because it looks like the dependent and the independent are the wrong way around, but it doesn't really matter. They're just letters that represent numbers. This is if and only if f of x is equal to y for all x in the domain A and y in the range. So that is the definition of an inverse, and it exists without any ambiguity or problems if and only if you're a 1-to-1 function. So this really is exactly the picture I drew at the top. Completely identical, right? This is a very precise statement for this original picture. That's exactly what this is saying. This is true of any x in the range and any y in the domain. So maybe I'll just copy this and bring it down, just because it's so crucial. So it's this picture. Now, a really important property of this is something called the cancellation property, which is something we've already seen with respect to logarithms and exponents. So this is very important. Very important. If you have an inverse function, you have the cancellation properties. There's two of them. So let's take a moment to look at this. If I start with x and I do the function f, I go across here, and then I do the function f inverse, I get back to x. But what does it mean to do a function and then another function? It means to compose. So you can see from this picture that if I start with x and I do f first and then f inverse, so that would be the composition of f and f inverse, I must end up back at x. So essentially f inverse is cancelling off the f if you want. So this is for all x in A, the domain of f. But the other way around is true, in the sense that if I started at y here, and I did the inverse first to get here, and then if I did the inverse first to get here, and then I did the function, I'd get back to the same point. So it would be cancellation again. So what does that mean? Well, now I'd be doing the inverse first. So it would be the composite the other way around. And what does it do? It just sends y back to itself for all y in B. So really what this is saying is the following. In a slightly more fancy terminology, I won't dwell on this, but f inverse composed with f either way round gives something called the identity function, which just sends the input to the same output. So x goes to x or y goes to y. Totally identical. So these are very important. They're very useful and they turn up all the time. So the cancellation properties. We're going to see once we look at exponential and logarithmic functions. The standard kind of cancellation properties we saw for logarithms and exponents are just examples of this. Okay, so let's do a couple of examples, shall we? This is a pretty abstract idea. We need to get our hands on what inverses look like. So the first one, I'll just kind of give it to us straight. So imagine I have f of x is equal to x plus 1. This is certainly 1 to 1. Okay, it's a straight line with slope 1, so the horizontal line test holds. So it has an inverse. It's kind of obvious what the inverse is here. You need to undo this. So to undo plus 1, you just do minus 1. So it turns out the inverse is equal to x minus 1. We'll discuss how to calculate inverses in a little second, but let's just check the cancellation property holds. So let's check both ways round. So if I was to do f, what am I doing? F inverse composed with f x. Okay, so what's that? So it's going to be f inverse f of x. I'm going to write this terribly carefully. This is f inverse x plus 1. So that's going to be x plus 1 minus 1. It's x. Tick, right? That's the same as that, exactly as we want. But I want to do it the other way around. Let's do it the other way around. So let's do f composed with f inverse. We need both of these to be true. So rather than write y, let's just write x. There's no point doing it the way around. I just need to check it's the same thing. So this is equal to what? F with f inverse x fed into it. So that would be f with x minus 1. That's x minus 1 plus x. That's equal to, sorry, it's plus 1. That's equal to x by the associative property of addition. Nice. Second example. I don't know, f of x is equal to x cubed. This is 1 to 1. It's kind of our main example we saw when we were doing 1 to 1 functions, just introducing them. And the inverse is exactly what you'd expect it is. The inverse is equal to the cube root. Works perfectly. Very nice. Now, as a warning, x squared can cause terrible problems. So we know x squared is not 1 to 1. X squared isn't 1 to 1, so it can't have an inverse function. For exactly the reasons I talked about, where would 1 go to? Is it plus or minus 1? So I mean, it does not emit an inverse function. But you could say, well, what about square root of x? So let's think about square root of x and why it's not a true inverse function. So square root of x is not a true inverse. So what's the problem? Well, the thing is, x squared, for it to be a true inverse, well, there's several things that would have to be true. First of all, what's the domain of x squared? It's all real numbers. So that would mean the range of the inverse would have to be all real numbers. But that's not true of this. It's only the positive numbers. That's the first issue, right? Next, you wouldn't have the cancellation properties holding. So just as an example, if I was to do, so I can do this a moment ago, but I'll do it again. If I was to take -1, and then I was to do the function x squared, so of course I'd go across to 1. But then if I was to do the square root, no good, right? It doesn't come back to the position you want. It comes back to 1, doesn't it? Because by assumption, you're always taking the positive option of the two square roots, sorry. So that's no good. So in terms of the cancellation property failing, what it's basically saying is the following. If I was to do -1 squared and then I do the square root, this is me really doing it numerically. If I was to do the square root of this is equal to 1. That's not equal to -1, which is what you need, right? The cancellation property says you get back to the same start point. The cancellation property is not true. And again, before you say, what about plus minus square root? That can't be an inverse because it's not a single output. It's not even a function. Okay, so next time we will see there is a partial fix to this. There is a partial fix to this, but it requires messing with the function x squared a little bit.